This video is going to be the last about the binomial distribution. It's going to provide a real-world example. Now, the example can get a little complicated in any example in the world of statistics can get a little complicated in the real world, but I think this one is tangible enough that we can see the benefits of statistics from pretty early on in this class. So we're going to follow along with a DNA matching example from the blog Freakonomics. So I've pulled up the web page here so that you can either copy the URL down or you can at least just Google Freakonomics and the title of this post and find it fairly quickly. I encourage you at this point to pause the video and go read this article to the best of your abilities. It's not an easy read, but at least gives you the idea that the FBI at various points in its work is interested in trying to match DNA across individuals, and they usually consider it 2 individuals at a time. So there are some percentages and calculations that happen mostly in these 2 paragraphs here. We are going to first introduce this problem as the FBI treats it statistically, and then we will jump into R to explain how these calculations are being performed. Okay, here we go. DNA matching. So if you don't know, DNA consists of 4 what are called base pairs. Let's just say 4 base pairs. A, C, G, and T. So like all of humans are basically composed of, I'm going to go with billions of base pairs that look like this in some complicated world of biology/chemistry that I really can't speak much about. So at any given site along our genome, there might be positions. Let's just say 5. And I don't know, they might go A, T, G, C, T. So this could be individual 1. And individual 2 might look something very similar for those same 5 base pairs, but they might have slightly different values. So we can turn this into a binomial problem by asking, of the 5 base pairs, how many match? When they match, we'll mark it a 1, and when they don't match, we'll mark it a 0. And we've thus created a sequence of Bernoulli observations. And there is some underlying probability P that any 2 base pairs match for 2 randomly chosen individuals. So this sequence of Bernoulli observations fits pretty well the definition of a binomial. So if you take these 5 and you sum them up, you get out 3. A binomial observation where capital K is equal to 5. So of the 5 base pairs, it turns out that individual 1 and 2 here match at 3 of the 5 sites. Okay, that's probably as good an idea I can give you of what this blog post is talking about as far as my understanding of DNA goes. So we're going to be creating a binomial out of matching base pairs across 2 individuals. So the first number I'm going to point you to is this 7.5%. That is the probability P that any two individuals match at a particular location. Now, I don't know where they came up with this 7.5%. That's beyond me in the world of genetics. But we will use that in our calculations. So the next thing is they calculate the chance that any two random people would match at all 13. So we used 5 in our previous example, but they're going to use 13 locations. So here we go. We can do that calculation using the binomial density function. So over here in R, I'm not even going to make a script out of this. I'm just going to immediately jump into the console. We're going to use the function that starts with the letter D for density, and we're interested in the binomial distribution. Now they're interested in 13 out of 13 locations matching with a probability of 0.075. That's that 7.5% chance. What we get is this incredibly tiny number. Please refresh yourself on scientific notation. This is 2.375726 times 10 to the power of -15. So there's essentially 14 zeros in front of this 2. So it's an incredibly tiny number. It's like 0.14 zeros and then a 2. That is 0.14 zeros and then a 2. So that's our calculation. And they say that any two random people should match at all 13 loci is about 1 in 400 trillion. Okay, so let's see how close our calculation comes to there. 1 in 400. Okay, we got 100,000, million, billion, trillion. Good Lord. Oh. So remember how small these numbers are. Our calculation using the binomial distribution is exact, and their rough estimate of 1 in 400 trillion is super close. Look at that. That goes point and then 14 zeros and then 25. And ours goes point and 14 zeros, 23. Now, you got to remember here that the U.S. made it to the moon using only 3 decimal places. So to match at the leading 15 decimal places is pretty significant. Okay, let's clear a little space so we can do one more of these calculations because they're kind of fun. Okay, next up, next sentence. They say if you choose exactly 9 locations for the two random people to match, the chance that they will match at all 9 is 1 in 13 billion. So we'll do pretty much the same thing as before. D for density, binom for binomial. So this is the density function of the binomial distribution. And we're going to do a similar sort of thing. And that's 1 over 13,000 million billion. Whew. That is close. Their approximations are quite close to our actual calculations. This is the binomial example, providing probabilities that any two individuals might match at 9 out of 9 locations. So if there were like 9 positions in front of you, 2 individuals would match at all 9 of them with this probability, so long as there was a 7.5% chance of matching at any individual position. Okay, one more calculation and then we'll call this video done. So under these assumptions, how many pairs, base pairs, would we expect to find matching on at least 9 out of 13 locations in the Arizona database, which consists of 65,000 people? So if there's 65,000 people in the database and they're comparing every 2 people in the 65,000 database, they're going to end up doing this many comparisons. So let's just go ahead and steal that number. Give ourselves some new space. And we'll multiply that by d binom of 9, 13, and 0.075. And now this time it's 9 out of 13 because they're specifically asking for matching 9 out of 13 locations across this many people taken pairwise. So all 2 people in 65,000 2 people, all combinations of 2 people in 65,000 people. If you don't immediately understand this calculation, please join the club and we will discuss once we get to probability how these sort of calculations show up. But if you don't immediately get this, don't worry. I didn't immediately get it the first time I saw it either. I had to think about it for a little bit. And we will cover calculations like that later on this semester. So our question is, how close is this number to 100? And not very, because there's commas in our numbers. Let that be a lesson to you. No commas in our 83. 83 is a pretty rough estimate of 100, but remember, he's saying remarkably, it's about 100. The exact calculation is about 83 matches. I didn't provide much context for these 3 numbers, but I leave that to you to read the article yourself and then see that the binomial distribution is in fact the way they are making these calculations. The binomial distribution is an incredibly powerful and useful tool in the real world. I hope this video helped you see that.